So with our diagonalization problem here, we're working on building the diagonal decomposition, which says again that as long as you have n linearly independent eigenvectors, then A can be decomposed into a product of three matrices. So we do see that 1, 1 and negative 1, 1 are linearly independent. We see that there's no scale factor that gives you one from the other, and therefore they are linearly independent. And so we just wanted to make sure that our columns, again, it doesn't matter what order you list your eigenvectors in, probably whatever one you call v1 goes first, v2 goes second, but then you need to make sure your corresponding lambdas are along the diagonal. So if this is v1 and v2, then this needs to be lambda 1 and this needs to be lambda 2. If you switch these two vectors, you would need to put negative 2 up here and put 6 down here, because the column corresponding to the eigenvector needs to have the corresponding eigenvalue along that diagonal element. You will get the same answer. It will still decompose, and the decomposition is not unique. So the last thing we need is to compute x inverse. And you can do this in your calculator. You just put this matrix in and then raise it to the negative 1 power. And we should get 0.5, 0.5, so 1/2, 1/2, negative 1/2, and positive 1/2. So we're saying that A is equal to x dx inverse. This is going to be our check to make sure this works out. So for x, I'm going to put in the 1, 1, negative 1, 1, the D matrix, which is 6, 0, 0, 2, and the x inverse matrix, which is 1/2, 1/2, negative 1/2, and 1/2. And if I do multiply these together, I encourage you to put this into your calculator and see that it does, but you will end up getting the original A matrix back, which was our 2, 4, 4, 2. Here, if we multiply these two first matrices, we'll get 6 times the 1, 1 matrix plus 0 times this, 0 times this vector, 2 times negative 1, 1, which is negative 2, 2. And when we multiply that by 1/2, 1/2, negative 1/2, 1/2, 1/2, 1/2 will scale this column, which is going to give us 3 for both the components. Here we'll have plus 1, here we'll have minus 1. So that will give us, let's see, 3 plus 1 is, or sorry, 3 minus, but of course I had to make a mistake, so this should be a negative 2, because that's our eigenvalue. I just didn't copy that sign down, and so this should actually be negative 2 times this will give us a plus 2 here and a minus 2 here. So 1/2 of 6 minus 1/2 of 2 is going to give me 3 plus 1, or 3 minus 1, which is 2. 1/2 of 6 is 3, negative 1/2 of 2 is 1, 3 plus 1 is 4, and you can see where this is going. We're going to get 2, 4, 4, 2, which does indeed work out. So if you had instead reversed the columns, if you had switched the v1 and v2 in this matrix, as long as you switch not these two columns, but another way to do this would be to write negative 1, 1, 1, 1, and then instead of putting 6 at the top left, you'd put negative 2 here, and then 6 at the bottom. So again, this is v2, v1, and this would be lambda 1, lambda 2, lambda 1. And then we would need the inverse of this matrix, which should not change it by much, but we will get some different values in there, which will be negative 0.5 for the x, for the top left component, 0.5, 0.5, 0.5, and you can see that when you multiply this out, you'll also get 2, 4, 4, 2. So why is it true that this works? Well, it's true because if we start off writing A, let's think about A as a 2 by 2. This will apply to 3 by 3s and 4 by 4s as well. X is going to be 2 by 2, D is going to be 2 by 2, X inverse is going to be 2 by 2. They have to be. And you're only going to have, for a 2 by 2, 2 eigenvalues, so you're only going to have 2 diagonal elements. So first of all, the one thing that we know is that if I take A times V1, that's going to give me lambda 1 times V1. If I take A times V2, that's going to give me lambda 2 times V2. Now let me go ahead and put these in a matrix. So the first column of my matrix is going to be A V1. So that's a column right there. The second column is going to be A V2. That's a column because that will give me another vector, right? And what vector will that give me? That will give me lambda 1 V1. So A V1 will give me a scaled copy of V1. That's going to be a column. A V2 is going to give me lambda 2 V2, which that's going to be the second column in there. And then what I see that I can do here is when I form new columns, I'm going to argue that this is the same thing as taking A multiplied by the matrix that contains two columns, one of which is V1 and the other which is V2. And the reason you can think about that as being true is if this itself is a column, and this itself is a column, and then A is a matrix, the components of this column are going to scale these two columns, and that's going to form the new column in our matrix, which is AV1. And then we'll take V2, those two components, scale them onto these two vectors. That's going to give us AV2, which will be our second column. For lambda 1 V1, this is a little bit less obvious to see, but if I write V1, V2 in a matrix, so those are the columns of my matrix, and then what I do is I write a matrix with lambda 1, 0, 0, lambda 2 here like this, and you can see this multiplication will be lambda 1 times V1. That's a whole column right there of values. That value right here is going to scale that column. 0 is going to scale that column, and that's going to give me lambda 1 V1. So what I'm doing is pulling this apart into two separate matrices. Here I'll have 0 and lambda 2. 0 will scale V1 plus lambda 2 V2 will give me lambda 2 V2. Now, by definition, this is just a matrix with the two eigenvectors in it, so that's the X matrix. This is the same X matrix here, and this is that matrix that we're calling D, so we have times D. Now, right now, it's the equation that we've developed is AX equals XD, but I want to solve for A in this equation, so if I multiply both sides by X inverse on the right, then guess what we have? We have our decomposition. This right here gives us the identity. A times the identity is just A, and we have A equals XD X inverse. But we should make a note here. This is true as long as A has an inverse. Sorry, as X has an inverse. Well, how do we know if it has an inverse? Well, we need to make sure we have that X has linearly independent columns. The columns are eigenvectors, so we need linearly independent eigenvectors, and that's exactly what the theorem requires of us. So this is the derivation for why that can be done. So the question is, why would you do it? Well, a really good practical use, in addition to showing us later on in the next lesson that this explains why multiplication of a vector that's not an eigenvector repeatedly by A will rotate that vector in the direction of the dominant eigenvalues eigenvector. Another practical implication for this is suppose you have a really large A matrix that's n by n and you want to raise it to a really large power. For computers to do this, it's still an incredible amount of arithmetic. And let's imagine you have a million by million matrix raised to the 100th power. That requires a lot of computation. However, it turns out that a diagonal matrix is easy to exponentiate. So this problem. Let's just look at d squared, d cubed, and d to the fourth. So 6, 0, 0, negative 2 squared will be 6, 0, 0, negative 2 times 6, 0, 0, negative 2. So 6 will multiply the first column. 0 will multiply the second column. Now move on to the next column. 0 will multiply the first column of the first matrix. -2 will multiply the second column. And you can see that what happens, or what emerges out of this, is that we get 6 squared, 0. We'll get 0 times 6 minus 2 times 0 is 0. 0 times 0 minus 2 times 2 is really -2 times -2, which is -2 squared. So on first appearance, it appears that if you have just elements along the diagonal and then zeros everywhere else, that exponentiating that is just a matter of raising the diagonals to a power, which is not true if these aren't zeros everywhere else. And if we do d cubed, 6, 0, 0, -2 cubed, well, so that we don't have to multiply 3 matrices together, that's 6, 0, 0, -2 squared times 6, 0, 0, -2 to the first. We can add those powers. And so we know that this is 6 squared, 0, 0, -2 squared. And we're going to see that when we multiply again by the same matrix, we're going to get 6 cubed, 0, 0, -2 cubed. And so the general observation that we can make is that if you have a diagonal matrix and you raise it to a large power, if you have 6, 0, 0, -2 to the t power, we can probably generalize and say this is going to be 6 to the t, 0, 0, -2 to the t. Now these are the eigenvalues. So later on we'll discover that because this guy is dominant, if you raise this to a really large power, it's going to blow up much faster than raising -2 to that same power, because it's all smaller. This is a larger base, so this is going to grow much faster, and this will help us later explain why it is that the vector that we multiply by a repeatedly starts to point in the direction of the eigenvector. This leads us to something bigger. So we said that if you wanted to take a to a power, normally you'd have to multiply a by itself. But because a squared is a times a, and a is equal to x dx inverse, multiplied by x dx inverse, I don't need the parentheses there because matrix multiplication is not commutative, but it is associative. And what I see in the middle here is that I have an inverse times its matrix, and that's the identity matrix. Therefore, I get x d dx inverse. And d times d is d squared. And hey, wait, that's a really easy thing to do because it's a diagonal matrix. All I have to do is square its diagonals and then multiply by 2 other matrices. To get a cubed, you can imagine what this is going to look like. This is a times a times a, which will be x dx inverse times x dx inverse times x dx inverse. Here I'll have the identity. Here I'll have the identity. That will give me x times d times d times d times x inverse. D times d times d is d cubed times x inverse. And we've got a beautiful observation here. A very easy thing to do. The diagonal matrix will take up the power, or be raised to that power, and x inverse are, they still require some computation time, but I no longer have to multiply a lot of matrices together because now we can generalize and say that a to the t will be x times d to the t times x inverse. This is not a transpose, but if this is a million here, then all I have to do is raise all the diagonal components of d to the 1/millionth power, zeros everywhere else, and this is relatively easy to do. So that's where the power of this method comes in. The bottom line, diagonalization makes it efficient to compute matrix powers. There is more. Let's look generally at the vector expansion of a to the t equals x d to the t x inverse. This will lead us to our next lesson in which we show why the dominant eigenvalues rule our world. See you then.